In this video, we are looking at ozone in the Earth's atmosphere over the poles, starting here with the South Pole. The ozone data we are looking at come from a model run by the Copernicus Atmosphere Monitoring Service, based on data from satellites such as EUMETSAT's METOP weather satellites. The reason we need to monitor ozone is that it is really important for life on Earth because it shields us, but also animals and plants, from harmful UV radiation from the sun. Over at the South Pole, in the early part of the year, it is continuous daylight and the ozone concentration in the stratosphere is kept at a relatively constant low level, as sunlight causes the ozone molecules to break up into oxygen atoms and molecules, and back again to reform ozone. In this process, the harmful UV light is continuously removed and doesn't reach the Earth's surface anymore. The same happens at any other place on the Earth during the day. When we move into May and the start of the winter period in the South Pole, with up to 24 hours of darkness, we start to see ozone levels slowly increase in the absence of sunlight. This means that we should expect the ozone levels to be highest at the very end of the South Polar winter towards September, after 2 to 3 months with very little sunlight. However, in early July, something very peculiar happens. A hole in the ozone layer above the South Pole starts to evolve, as you can see in the video now. And indeed, this hole in the ozone layer never existed in the South Polar region in this form before mankind started industrial processing. The reason which triggered this hole to form is mainly the injection of chlorofluorocarbons, or CFCs, into the atmosphere over the last century. CFCs were used in refrigerators and air conditioning systems for years, until they were banned by the Montreal Protocol in 1987 because of their only then known effect on ozone. Unfortunately, there are still a lot of these very stable CFCs in the upper atmosphere, and in the very, very cold winter conditions during the polar night, CFCs break down on the surface of very thin and icy polar stratospheric clouds, which form mainly in the South Pole during this period, releasing chlorine molecules. Due to a set of complex but very stable wind and temperature conditions forming over and around the Antarctic continent during exactly this period in time, these chlorine molecules finally come into contact with the ozone layer and effectively break up the ozone molecules, creating a deep hole in the ozone layer, eliminating its shielding effect. During the twilight conditions in early Antarctic spring, the ozone layer slowly closes and it starts to work again as a UV shield towards the end of the year. The extent of the yearly Antarctic ozone hole has been decreasing over recent years as the amount of CFC chemicals in the atmosphere reduces. But scientists still think it is likely to be many years before the annual hole has become a thing of the past. This mechanism of ozone hole formation is so unique and so specific to the Antarctic conditions that only under much rarer conditions and for much shorter time periods do ozone holes develop over the North Pole. And if they do, they are usually significantly smaller in the extent. But as you can see here in the video, when they form, these very low ozone levels can quickly reach areas with very large populations and are therefore much more dangerous for human health.